Hello, in today's video we're going to talk about turbojet engines, another classification of air-breathing propulsion devices for airplanes. These tend to be used in more higher performance aircrafts than, let's say, a turbofan engine, but they're pretty simple in their operation. So here I have this is a cross-section of what a turbojet engine would look like. So this is the outside of it. And then these are fans, kind of there. So let's go through this. All right, so we have the intake. So air comes in, is diffused to slow it down a bit, and then it goes through, and we have the states down here. So it goes through the diffuser to kind of slow it down, and there's fan blades spinning right here that are driven by the turbine back here. So I guess if you were to start up the engine from a cold start, from not running at all, obviously there's no air flowing through, so you start spinning the turbines with some auxiliary power, which starts the compression, and then air starts to get sucked into the engine, then it's lit, and then once you're going, then it's good to go. You don't need any forward velocity like a ramjet to produce thrust. You can produce thrust from zero velocity as long as you can suck air into the intake. So back here, okay, it goes to the diffuser, slow it down, gets compressed, the temperature increases, pressure increases as you compress the gas. Then it kind of just flows through the compression cycle, and not only is there compression from the fans spinning and compressing the air, and also the inlet, or the compression, the area that the air goes through gets smaller, so it compresses that way. So then it goes through and then into the combustion chamber, where it is mixed with fuel and then, lit on fire. Obviously increases temperature greatly, and so then it throws it out the back. But first it goes through a turbine right here, which provides the energy for power on the aircraft and also to spin these compression blades up here. So it has a bunch of functions. And then the air goes out through a nozzle where it expands to the nozzle and then out the back, and you have propulsion. But you can also include a afterburner, as I showed the states down here. So imagine, right here it ends with the turbine. But if you added an afterburner, this would continue on. Oops, pen is not working. So it would continue on, and there'd be another flame holder, and so it'd be more flames right here to light it. But you also are mixing it with more fuel. Add more fuel, light the gas again through the burner, and then it goes out through the nozzle at higher velocities. Now you produce much more thrust. So a lot of like fighter jets, they'll turn on the afterburners to like take off or kind of get through like the sound barrier, turn on the afterburners. But the thing with the afterburners is that it takes a ton of fuel, and it's not very fuel efficient, but you do produce a lot of thrust. And we're going to do a calculation where with a turbojet, with an afterburner, so you can see how much more fuel is used. And as you're analyzing the turbojets, we have the cold section and the hot section. So cold is anything before the combustion chamber, because that's the cold air. And even though it heats up through the compression cycle, it's not as hot as it is when it's lit or it's combusted. So everything after the combustion chambers are hot, obviously, and then we can even have a different temperature range for the afterburners. Now this can be a different set of gas. We would call it like gas properties. There could be another section of gas properties for the afterburner. So we have our states here. So one more time, you have your state A, which is your atmospheric conditions. State 1, right before the diffuser. 2, right after the diffuser. Compression, state 3. Combustion chamber to state 4. mass flow rate of fuel, mass flow of air up here. Turbine, now if there's an afterburner, you have more fuel, another combustion in the burner, and then a nozzle, and then the exhaust exits. So pretty simple. Now let's do a problem where we can analyze the temperatures and pressures, all these states, and calculate the impulse, and all that kind of good stuff. Alright, so for our example problem, we have a turbojet with an afterburner that has all these conditions. So it's flying at Mach 0.95. The pressure ratio of the compressor is 10. These are all the specific heat ratios, gas constant, atmospheric conditions, and then we have a whole bunch of efficiencies, pressure ratios, temperature ratios, and the heat of combustion. So let's just start analyzing these numbers here. So let me move this up. So we have the temperature at state 1, which is TA, 1 plus gamma C minus 1 divided by 2 MA squared. Okay, so a couple things to note. See, we are using the cold specific heat ratio. And if you plug in the numbers, we have all the values for this. Get 254.988 Kelvin. So the temperature does increase a little bit as it goes from atmospheric to state 1. And then the pressure at state 1, using this equation, again using the cold specific heat constants, plugging in those numbers, we get 16,000. About 16,000 pascals. So again, pressure increases at state 1. Now the temperature at state 2, you can say equals its temperature at state 1. So as it's going through the diffuser, there's no increase in temperature, so we don't have to worry about that. But there will be a pressure drop through the diffuser because it is not an ideal turbojet. We are not dealing with an ideal turbojet. So the equation for that, my pen is not working very well. You get 1 plus efficiency, this is the efficiency of the diffuser, times the cold specific heat constant. I'm going to get a new pen, hold on. Cold specific heat constant. Come on, pen, work. Okay, 1 plus gamma C minus 1 divided by 2 times MA squared. All this raised to gamma C. Plug all these values in, we have them all. At 0.989. Now we can calculate the pressure across the diffuser. So that's pressure drop across the diffuser times PO1, and that equals 15,915.42 pascals. So as the air comes in, so there's a little intake right here. So there's a little. So as it gets to right before the diffuser, it heats up and the pressure increases. As it goes through the diffuser, temperature stays the same, pressure decreases a little because it's a non-ideal turbine. But now the pressure is going to increase a lot going through the compressor because it is compressing. So pi C, temperature ratio, that's a value of 10. So you multiply the pressure of 2 times that pressure ratio, and you get a much bigger number, 159,154.2 pascals. Now that makes sense, getting pressed, obviously it's going to increase in pressure. Actually, let me go back here. So what we're trying to find is we're going to eventually find the impulse, thrust specific fuel consumption, thermal efficiency, propulsive efficiency, and the overall efficiency. And then we're also going to find the optimal ratio for the compressor. Because 10, where it's just a given number, we're not sure that's optimal. We're finding the conditions if that pressure ratio is 10. So then we have our equation for TO3, which equals tau C, so temperature ratio across the compressor. And then tau C equals 1 plus pi C gamma C minus 1 divided by gamma C, then all of that minus 1 divided by the efficiency of the compressor. That equals 2.276. Therefore, TO3 equals 580.31 Kelvin. So, as the gas is getting, air is getting compressed, it also heats up. And that makes sense. Oh, but we use the efficiency of the compressor. My bad, I forgot to write the equation for the efficiency of the compressor, which equals pi C to the gamma C minus 1 divided by gamma C minus 1 pi C to the gamma C minus 1 divided by EC gamma C. So this EC, sorry if you can't see it, that's the isentropic, oh, I just had the word for it. It's polyotropic efficiency. All that minus 1, so that equals 0.7295. And then you plug this back into there, and then you get that value. Moving on, lots of things to calculate. So we get TO4 equals this times TA. So, and we have that as 6. So it's going to be a hot temperature. So now we are efficiently in the hot temperature range if we have to use a specific heat ratio. PO4 equals pressure ratio of burner. So the pressure ratio across the burner combustion chamber, that the pressure drops a little bit. And now we're going to calculate the specific heat count, or the specific heats for all these. So this would be hot, hot, hot. Also it can be written as the turbine. Plug in all these numbers. That's 43.7 joules per kilogram Kelvin. So this is gamma equals 1.3. CPC, so that's the cold. This is gamma equals 1.4. All that equals 1004.5 joules per kilogram Kelvin. Now, for the afterburner, just because we're here, let's calculate that. So this is gamma equals 1.2. S equals joules per kilogram Kelvin. So now we can find the fuel to air ratio for the burner. So this is the first combustion chamber. We use this equation here. We have all these values. We know all these. But also because we wrote this as 43.5 megajoules per kilogram. Make sure to convert that to joules per kilogram. Once you do so, you get 0.0251. So not a ton of, not a very high fuel to air ratio. So that's good. That's what we want. So now we calculate temperature at state 5. And the equation for tau T equals 1 minus CPC TO3 minus TO2. All that divided by 1 plus FB CPT TO4. That equals 0.800. Therefore, TO5, now we have tau T, we have TO4, that equals 1037.1 Kelvin. So now we can find PO5 pi T times PO4, h for pi T equals tau T to the gamma T divided by gamma T, or E T gamma T minus 1. So tau T raised to this polytropic efficiency of the turbine, that equals 0.3415. So as you can see, the pressure is going to decrease a lot as it goes across the turbine, which makes sense. Plugging in for pi T, PO4, we get PO5 equals 51633.6 pascals. And that makes sense that the pressure is going to drop as it's going through the turbine. So now if there was no afterburner, you could stop the calculations here and then calculate the temperature at the exit and the velocity at the exit using equations I'll show up here. But because of an afterburner, we do have to do more analysis. So now we're at state 7. Times TA, and we have all these values, we get 1944 Kelvin. Now this is going to be our hottest temperature in the entire structure, so we have to make sure that the materials we're using can withstand that temperature. So now we have PO7, we have all these numbers, get this equation. So now let's calculate, this is where it's going to get interesting, the fuel to air ratio of the afterburner. And we're going to see that it's much greater than just the regular turbojet engine with no afterburner. So this is our equation. Once you plug in all of those numbers, you get 0.0531. Now comparing that to the other fuel to air ratio, it's like almost twice the value. Pretty crazy. Now we calculate the exit temperature, which is the temperature at the exit, temperature at state 9 equals TO7 times 1 minus the nozzle efficiency, 1 minus PA divided by PO7. So this is the PO, that means stagnation or total pressure. And then we're at the gamma exit, minus 1 divided by gamma exit. So now we're using the specific heat ratio of 1.2 because we're now at the afterburner states. And that equals 1484.2 Kelvin. So now we can use that value to calculate the velocity at the exit, which equals V9, which equals square root 2CP the exit, TO7 minus T9. We have T9. The CP at the exit is the CP at the afterburner, and that equals 1,258.4 meters per second. Now, if you wanted to find the temperature at the exit with no afterburner, you would substitute PO7 for PO5 and get that value for the type T exit there. And then for velocity, you'd use TO5 minus whatever the new value for T9. And you would use the CP for the turbine, gamma for the turbine. Well, now we're going to calculate the exit velocity. Now let's calculate just quickly the entrance velocity of the air, which would be ma times AA, which equals ma times the square root of gamma cold times RTA. We have all these values, we have 279.869 meters per second. So we can see the difference between the entrance velocity of the air versus the exit velocity. So it's speeding up the air quite a bit. Now let's calculate the exit Mach number for fun. VE divided by AE equals VE divided by the square root of gamma, the exit, R times T exit. So this is again that gamma A afterburner, temperature of the exit, which is that. I have all these numbers, 1.76. So Mach number of air coming out of this thing is quite large. All right, we're almost done with the last home stretch of things. Calculate. So the total fuel to air ratio equals F, which equals FB plus FAB, which equals 0.0782, which is quite large. We can calculate the impulse using this equation, and we get 1,076 Newton seconds per kilograms. Quite a large impulse, which is what we want. We want to, with a turbojet with the afterburner, right? We want a lot of energy. But this thrust specific fuel consumption, which equals F divided by I, probably going to be quite large too. So we are using a lot of fuel to get that specific thrust or impulse. But that's a worthy trade-off in this situation, right? Because we need the thrust. So we're going to trade off a little fuel. Now we calculate this value for R, which equals VA divided by VE, that just equals 0.2224. Then we calculate the thermal efficiency using this equation, and these efficiencies aren't going to be very high. And that would equal 0.2395. And we got the propulsive efficiency equals 2R 1 plus F minus R divided by 1 plus F minus R squared. We have all these values, 0.3700. Therefore, we can get our overall efficiency. And that will equal 0.0886. So not very high. But now we want to calculate what would be the optimal pressure ratio across the compressor. And let's see what that is. And then we're also using gamma cold for that, because we are dealing with a compressor, which is a cold air. And then plugging all that in, you get 14.68. So if we wanted to go back, do all these equations again, except using a pressure ratio of the compressor of 14.68, hopefully we'll see that these efficiencies then increase using our optimal compression ratio. So that's it for this video. If you got through it all, you probably didn't, but there you go. Those are the basics of a turbojet engine and how to calculate all the properties at each state. So there you go.